The following demonstration provides a comprehensive overview of the process for performing a filter integrity test on a cleanroom ceiling using our core product, the RSF. In this presentation, we will explain each stage of this innovative and time-efficient process, including the preparation, the execution of the automated measurement process and the creation of the measurement report. Smart Cleanroom Solutions GmbH is a company of the Infrasolution AG. The main business focus is the development and production of automated robotic systems for the quality assurance of HEPA and ULPA filters for cleanroom applications. The product family AutomaticParticleScanSystems provides an automatic measurement process according to ISO norm. Vertical and horizontal laminar flow systems and terminal filters can be tested with RobotScanFlex. Filter integrity tests in hot air sterilization tunnels are performed using LinearTwinScan. The latest development, IntegratedRobotScanFlex, aims at qualifying open and closed RABS and isolators as well as safety cabinets. The main component of the Automatic Particle Scan System RSF is a three-jointed robot arm, the SCARA robot arm. All robot systems from the Smart Cleanroom Solutions GmbH include the two subsystems control box and raw gas module as well as a tablet with the ScanWare and ScanWorx software packages installed. The RGM is used to generate and monitor the DEHS test aerosol, which is applied upstream of the filter element. The aerosol concentration is automatically controlled by the RGM and can be monitored and adjusted using the ScanWare software. The control box is the central component of the system and forms the interface between all electrical, electronic, and mechanical units of the system. The stand is adjustable in height to suit to the environment and can be extended up to a height of 4 meters. The robot systems are controlled using a tablet to set up and start the measurements. It can also be used to view the results live and monitor the measurement. A three-armed SCARA, which scans the filter elements in a meandering path, forms the main component of the RSF system. The robot arm of the SCARA has a maximum range of 1,850 mm and is controlled by the CBOX. It is also possible to attach probe tubes of different lengths to the tool center point in order to adapt the robot to the local conditions. The ScanWorx software package is used to prepare the measurements during pre-processing and to evaluate and log them during post-processing. All relevant data for a measurement protocol are stored on a USB stick during the measurement. After a measurement has been completed, the measurement data is summarized in a digital measurement report. This report contains a detailed list of the measurement results, a 2D heat map and the devices that were used, as well as all the necessary certificates. During pre-processing, the neutral filter files are generated for all measurements to be performed with RobotScanFlex. If filters are measured that have already been measured once, the neutral filter files can be read in again so that the pre-processing only has to be carried out once for each measuring point. A neutral filter file is required to collect all the information for the measurement. In order to carry out a measurement, we need a few parameters about the filter to be measured. This includes, for example, information about where the filter is located, the filter ID, what type of filter it is, and the filter dimensions. If all fields are filled in correctly, the storage folder for the neutral filter file must then be selected. These files are created in XML format and can have any name. For extensive measurement campaigns, a systematic naming of the XML files according to the scheme proposed here is recommended. Ideally, the data should be saved on the USB stick supplied for the upcoming measurements. Before the measurement can begin, it is important to prepare the robot for the measurement. We use the ScanWare software package to set up and perform the measurement. Each user receives their own access data to ensure secure and personalized access to the system. The neutral filter file created in post-processing must first be loaded into the ScanWare. The information about the filter to be measured is then entered on the left-hand side. Once the appropriate file has been selected, the user is asked to choose the norm according to which the measurement is to be carried out. Further data about the filter that is not listed in the neutral filter file should then be entered. The robot must then be moved to its starting position. This depends on the measuring environment and the possible obstacles that the robot has to overcome. The method chosen by the user to teach the robot also plays a role here. There are two options for defining the location of the filter in the robot coordinate system. With the help of a laser module, the robot is placed under the filter so that the center of the laser cross is located under one of the filter corners and is flush with the edges of the filter. The probe is located in the center of the filter box. To complete the measurement setup, you only need to specify how the filter is arranged in the coordinate system. The filter dimensions were read from the neutral filter file for this purpose. The particle counters can then be started and the aerosol loading can be set up. The measurement can now be started. This was the first way to set up the measurement. Next, we present the second option. Sometimes the robot cannot be placed directly under the filter because of obstacles. A filter framed by two walls is used for this demonstration. The robot is placed in its starting position and then aligned parallel to one of the filter edges using the laser. The current arm position of the robot is displayed on the ScanWare user interface. The rectangle that is to be scanned is now stretched out. Because of time reasons, only a section of the filter is scanned for the demo. To span the rectangle, 3 corner points of the filter must be marked in the robot coordinate system. The ScanWare helps the user to navigate to the corner points correctly. If 2 corner points are reached and saved, the coordinates of the third corner point are calculated automatically and can then be approached. Once all 3 points have been saved, the rectangle representing the filter can be spanned. The particle counters can then be started as announced and the aerosol load can be set. In the next step, the aerosol generator in the RGM is started, as well as the particle counter on the raw air side, which is responsible for monitoring the particle concentration applied to the filter on the raw air side. Aerosol load can then be set up and adjusted via the RGM. The nozzle pressure can therefore be set either manually or automatically. For the demo, it is set automatically. The desired load for the measurement can be defined on the right. On the left-hand side, the user can check the progress of the load and the nozzle pressure at any time. Once the loading process has been started, the actual value is automatically adjusted to the desired target value. In addition to the actual value of the load, the upper and lower limits specified by the norm are also shown, which must be adhered to in the event of fluctuations in the load. Our system is known for automatically adjusting the actual value back to the target value in the event of deviations from the target value. If the aerosol load has been correctly adjusted, the particle counter on the clean air side must then be started and the length of the probe being used must be specified. This completes the preparations for the filter integrity test and the measurement can be started. Once the measurement has been started, the probe gradually scans the filter area in a meandering pattern. For this demo, the filter was intentionally damaged to show the procedure in case of a leakage. The leakage is marked black in the filter. During the entire measurement, the user is able to see the measurement results in real time in the ScanWare. On the right-hand side, the incoming particles are counted and the limit values applicable to the measurement can be checked. On the left-hand side, the measurement results are visualized with the help of a heat map. Green indicates the areas in which few or no particles were measured. The more particles found, the redder the area, the higher the measured particle concentration. This can now also be seen in the heat map. The robot has measured an increased amount of particles exactly at the point where the filter was damaged. A potential leakage was found. Once the measurement has been completed, the heat map is scanned and the areas that might be potential candidates for a follow-up measurement are identified. In other words, where the particle concentration was very high. Remeasurements must be carried out for all areas that are above the limit value specified by the norm. If remeasurements are available, they are carried out automatically. The duration of the remeasurement can be set by the user before the start of the remeasurement. In this case, the limit value was crossed during the remeasurement and the measurement was therefore not passed. A leak was found at the position where we damaged the filter. The results of the measurement can then be saved on the USB stick. The user can optionally add a comment to the measurement. During post-processing, a measurement report is created from the data recorded during the measurement. The data stored on the USB stick is processed further for this purpose. The data of a measurement always consists of 3 individual files: a CSV file, an XML file and a checksum XML file. The name consists of the date and the start time of the measurement as well as the building, the room and the filter ID. In this way, unique names are always generated for a data log. To create the report, all 3 files of a measurement must be loaded into ScanWorx. It is possible to summarize the measurements of an entire room or building in a single measurement report. Before the measurement log can be created, a few more measurement data must be added. The assignment for the measurement and the test method used for the measurement. It is also possible to leave a comment in the protocol with information about the measurement. Documents can also be attached to the report. The user can decide for himself which documents are important. For example, the room plans or the certificates for the devices used can be attached to the protocol. Finally, the protocol can be provided with company logos, a signature, and a password. Once the measurements that are to form a report have been selected and the storage location determined, the measurement can be created. The devices used during the measurement are listed on the cover sheet of the measurement report together with their serial numbers. This includes, for example, the robot system being used, the particle counters and an aerosol generator. If a leak was found during one of the measurements listed in the protocol, this will be documented here. The date of creation and the name of the creator are also documented here. The first page of the protocol provides an overview of all measurements listed in the protocol. This provides information on the measurement duration, the particles measured and the integral leakage value. If a room plan has been attached to the protocol, this is shown on the following page. The room plan is followed by the measurement results including the corresponding head maps of the measurements summarized in the document. In addition to all important information on the measurement, it is listed here whether the respective measurement was passed integrally and locally. If there were re-measurement points during the measurement, this is marked accordingly in the heat map. The last pages of the measurement report then contain all the other attached documents, such as the certificates of the used devices.